Have you ever wondered how airplanes weighing tons of metal soar gracefully through the air? The answer lies in an invisible force airflow. By manipulating airflow, engineers have designed aircraft that can defy gravity and transport us across continents. From the Wright brothers' first successful flight in 1903 to the sophisticated jets of today, our understanding of airflow has been paramount in advancing aviation technology. By comprehending the principles of airflow, we can design aircraft that are not only capable of flight, but also safer, more efficient, and capable of incredible feats. Airflow is the invisible hand that guides aircraft through the sky, and its importance cannot be overstated. Airflow, the movement of air relative to an object, is fundamental to aviation. As an aircraft moves through the air, it disrupts the air molecules, creating a complex pattern of airflow around its surfaces. This interaction between the aircraft and the air is what generates the forces of lift, drag, and thrust. Understanding these forces and how to manipulate them is the essence of aerodynamic design. The shape of an aircraft, particularly its wings, is crucial in determining how air flows around it. Airfoils, the cross-sectional shape of wings, are carefully designed to create pressure differences that generate lift. The upper surface of an airfoil is typically curved, while the lower surface is relatively flat. This shape forces the air flowing over the top to travel a longer distance than the air flowing underneath. According to Bernoulli's principle, faster-moving air creates lower pressure, and slower-moving air creates higher pressure. Airflow over an aircraft's surfaces can be classified into two main types, laminar and turbulent. Laminar airflow is smooth and streamlined, with air molecules flowing in parallel layers. This type of airflow is characterized by low friction and drag, making it desirable for reducing fuel consumption and increasing efficiency. However, laminar flow is more difficult to maintain, especially at higher speeds and with increased surface roughness. Turbulent airflow, on the other hand, is characterized by chaotic and irregular movement of air molecules. It is characterized by eddies, swirls, and a mixing of layers, leading to higher friction and drag. While turbulent flow is generally less desirable than laminar flow, it can be advantageous in certain situations. For instance, turbulent flow can delay flow separation, a phenomenon that can lead to a loss of lift, especially at higher angles of attack. Engineers strive to design aircraft that maintain laminar flow over as much of their surface as possible to reduce drag and improve fuel efficiency. Lift is the aerodynamic force that counteracts the weight of an aircraft, allowing it to stay airborne. It is generated by the pressure difference created between the upper and lower surfaces of an airfoil, as explained by Bernoulli's principle and Newton's third law of motion. The shape of the airfoil, the angle of attack, and the speed of the aircraft all play significant roles in determining the amount of lift generated. As the angle of attack increases, so does the lift up to a certain point. However, if the angle of attack becomes too steep, the airflow over the upper surface of the wing can separate, resulting in a sudden loss of lift known as a stall. The speed of the aircraft also affects the amount of lift generated. This is why aircraft need to achieve a certain speed before they can take off. Drag, often referred to as the resistance to motion, is the aerodynamic force that opposes an aircraft's movement through the air. Acting in the opposite direction to the aircraft's velocity, drag is essentially a result of the friction between the aircraft's surfaces and the air molecules. Although drag is undesirable as it reduces fuel efficiency and limits the aircraft's speed and range, it is an unavoidable aspect of flight and must be meticulously managed through aerodynamic design. There are several types of drag, including form drag, skin friction drag, induced drag, and wave drag. Form drag, or pressure drag, is primarily caused by the aircraft's shape and size. To mitigate form drag, streamlining the aircraft's body, reducing its frontal area, and minimizing protrusions can be effective strategies. Skin friction drag, on the other hand, stems from the friction between the air molecules and the aircraft's surface. Thrust is the force that counteracts drag and propels an aircraft forward. It is generated by the aircraft's engines, which may be propeller engines, jet engines, or rocket engines, depending on the type of aircraft. Propeller engines generate thrust by accelerating a large mass of air rearward, while jet engines produce thrust by combusting fuel and expelling the hot exhaust gases at high speed. Rocket engines, which carry their own oxidizer, generate thrust by expelling the products of combustion. The amount of thrust required for flight varies with the aircraft's weight, speed, and aerodynamic characteristics. During level flight, the thrust produced by the engines must equal the drag acting on the aircraft. To accelerate or climb, the engines must produce more thrust than drag. Control surfaces are movable surfaces on the wings, tail, and other parts of an aircraft that pilots use to manipulate airflow and control the aircraft's attitude and direction. The primary control surfaces include the ailerons, elevators, and rudder. Ailerons, located on the trailing edge of the wings, move in opposite directions to control roll, which is the aircraft's rotation around its longitudinal axis. Elevators, hinged surfaces on the horizontal stabilizer at the tail, move together to control pitch, the aircraft's up and down movement of the nose. The rudder, a vertical surface on the vertical stabilizer, moves left or right to control yaw, the aircraft's side-to-side movement of the nose. Pilots use these control surfaces to maneuver the aircraft, adjust its altitude, and maintain stability during flight. By altering the shape of the airflow over these surfaces, pilots can generate aerodynamic forces and moments that control the aircraft's movement. Stalls and spins, when airflow goes awry. While airflow is essential for flight, certain aerodynamic phenomena can lead to dangerous situations if not properly understood and managed. A stall occurs when the angle of attack of the wing exceeds a critical angle, causing the airflow over the upper surface of the wing to separate. This flow separation results in a sudden loss of lift, and the aircraft can no longer maintain altitude. Stalls can occur at any airspeed and in any flight attitude, and they are often preceded by warning signs such as buffeting vibrations and sluggish controls. Recovery from a stall involves reducing the angle of attack below the critical angle, allowing the airflow to reattach to the wing's upper surface and restore lift. A spin is an aggravated stall that occurs when one wing stalls before the other, causing the aircraft to enter a rotating descending spiral. Advancements in aerodynamics. Our understanding of airflow and aerodynamics has advanced significantly since the Wright brothers' first flight, leading to remarkable innovations in aircraft design and technology. Computational fluid dynamics, or CFD, is a powerful tool that allows engineers to simulate airflow over complex geometries, optimizing aircraft designs for improved performance, efficiency, and safety. Wind tunnel testing, both physical and virtual, remains crucial for validating designs and gathering data on aerodynamic characteristics. Advancements in materials science have led to the development of lighter and stronger materials, such as carbon fiber composites, which allow for the construction of more fuel-efficient and aerodynamically refined aircraft. Active flow control technologies, such as boundary layer suction and blowing, are being explored to further reduce drag and improve lift. These technologies involve using small actuators to manipulate the airflow over the aircraft's surfaces, delaying flow separation and enhancing aerodynamic performance. The quest for more environmentally friendly aviation has spurred research into novel aircraft configurations, such as blended wing body designs and electric propulsion systems. The future of flight. The future of flight is brimming with exciting possibilities as our understanding of airflow and aerodynamics continues to evolve. Supersonic and hypersonic flight, once confined to the realms of military aviation and space exploration, are now being seriously considered for commercial applications. These high-speed flight regimes present unique aerodynamic challenges, such as shock waves and intense heating, requiring innovative solutions and materials. Unmanned aerial vehicles, commonly known as drones, are rapidly gaining popularity for various applications, including aerial photography, surveillance, and delivery services. The aerodynamic design of UAVs is crucial for ensuring their stability, maneuverability, and efficiency. As technology advances and regulations evolve, we can expect to see even more innovative UAV designs, potentially transforming industries and our daily lives. Electric and hybrid electric aircraft are gaining momentum as the aviation industry seeks to reduce its environmental impact. Conclusion. Airflow. The key to aviation. Airflow is the invisible force that shapes the world of aviation. From the fundamental principles of lift, drag, and thrust to the complexities of stalls, spins, and supersonic flight, understanding airflow is paramount for designing, building, and operating aircraft safely and efficiently. Advancements in aerodynamics have led to remarkable innovations in aircraft design, materials, and propulsion systems, continuously pushing the boundaries of flight. As we look to the future, our understanding of airflow will continue to be instrumental in shaping the next generation of aircraft. From supersonic and hypersonic flight to electric and autonomous aircraft, the quest for safer, more efficient, and sustainable air travel relies heavily on our ability to harness and manipulate the invisible force that lifts us up and carries us across the sky.